这课本吗？那是少的东西。哦，嗯，要确实是吗？一点应该是这个是 ring，所以叫 ring 是一的，是一点一，
这是11，
这是
啊对了，
找不到，
我看回到
我找一下。嗯，是减，有一个减，是1.1.7，一个减，
啊
我改一下。
啊，
Okay, we start. Um, and, if you see the assignment, see, okay, so just now Ziqian asked want to clarify about this symmetric group has three indexes. It's about the function composing, right? When you permit three indexes, like you have transposition 1, 2, 1, 3, 2, 3, 1, 2, 3. So show that this symmetric group have the relation by and relation. Okay. These two different presentation show that they are isomorphic. Okay. Yeah, show that they are isomorphic. And then there's a sum typo here, A union B and then A intercept B in question. So basically this is taken from the textbook. Okay, so there should be a minus here. I will fix this typo. Okay, yeah. So this is from the textbook 11.1.7. If you wonder, I will fix this typo. Okay, after class. Okay, if you have problem, please check with me. Okay. All right. So this is about assignment. Okay. Let's go through the definition of rings again. Let's go through the definition of rings again. Go through the definition of rings again. So what are rings? Again, the integer is an example of rings. Okay, but in general, rings is a set of elements. Okay, there are two ways to compose them. Right. So how you compose integer? You can add them. Okay, or you can multiply them. So there are two operations on integer. You can add, you can multiply. Okay, right. Then, what does this addition and multiplication need to satisfy? So under addition, you have to be a abelian group. Okay, you need to be a abelian group. In particular, the addition is commutative. And then, how about multiplication? Okay, we require multiplication to be just commutative and associative, and you have identity. That's all. We don't require inverses. Okay, not necessarily you will have inverse, multiplicative inverse. And then the third law, you need to tell me how I add and multiply when they come together. Okay, which we call the distributive law. This is what you did in the high school, right? When you open the bracket. Okay, how will you open the bracket? I put some remark in the lecture notes, so please check out. Oh, there's some typo here. Please check out. So first remark is very important that you distinguish between additive identity and multiplicative identity. Okay, so there are two identities inside the rings that you need to tackle. And then second, if your rings have multiplicative identity, sometimes in the reference you will see that this is a unique rings. Okay, maybe some rings don't include the multiplicative identity, but in our case we include. And the rings that we include in our definition is quite general, which is a commutative rings. For non-commutative rings, the multiplicative might not be commutative. We can throw away. We can just consider associative multiplication. Again, not commutative. There's no identity. Okay. So check out the definition of rings whenever you met rings. But this is most general one about commutative rings. So the commutative rings here, the commutative refer to the multiplication. Addition is always abelian under addition. And then last time we talked about this definition of subrings, right? Okay, what is a subring? Subring is a subset of ring that's closed under the operation of addition, subtraction, and multiplication, and that contains the element 1. Okay, like what I said last time, maybe we want to throw away the subtraction condition here. If I throw away the subtraction condition here, what do I add in? What do I need to add in to fulfill the definition of rings. Okay. If I were to remove the subtraction from the definition, I need to add in additive inverse for every non-zero element here. Okay, so for every non-zero element. Non-zero. Okay, in the subring. And I need to add in the additive inverse. Okay. Why? Because if I have operation of subtraction, what does that do? Okay. For example, I have x inside my subset, right? I can subtract x. So if x subtract x, what do you get? You get 0. So 0 will be inside my subring. Okay, if I add in the operation of subtraction. And if I can subtract minus x will become the inverse of x. Okay, so all the elements will have the additive inverse. Okay, but in other words, you can just say that a subring is a subset of ring that satisfy all the ring axiom. That one is it. If you don't want to talk about all these operations. Okay. Okay. This is similar to subgroup. What's a subgroup? It's a subset of group that satisfy group axiom. Okay. So similar to subring. Make sense? Does it make sense? Okay. Not just non-zero, but sorry, just every. 0 is it on additive inverse. Right? Okay. Yeah. Next, I give these examples here as a ring. What are rings? So Z confirm is a ring, integer. And then real number is also a ring. You can add, multiply all the inverses as this, additive inverse as this. And then multiplication is commutative. And what else? Multiplication is associative, right? It also distribute. You need to check all the property. How about ZP? Okay, ZP for P prime. Okay, so when P is prime. So I should say this P here, P is prime. Okay, last time we say that when does the ZP has a multiplicative inverse? Okay, when does the elements in ZP has multiplicative inverse? Okay, it's when all the elements is coprime to P. Okay, so to make sure that every element in ZP has multiplicative inverse, P has to be prime. Okay. Right, and then so continuous function also form a rings. Okay. So what's the product structure on the continuous function to give a ring? Do you have any idea? What product structure, what multiplication we can put on continuous function to form a ring? What can you try? No idea. Okay. 哲轩 what polynomial I want structure? I want multiplication structure. Multiplication structure. So how I combine two functions? What kind of operation you can combine two functions? How do you combine two functions? You can do addition, right? Okay, so addition of two functions. How to define addition of two functions? F plus G. How to define this? So you want to define the function, you need to define on points. Okay, so you need to tell me how it evaluates on points. Right? So how do I define this? I just simply define by fx plus gx, because I know what is fx, I know what is gx. Fx and gx are just some real number. I can add real number. So this is the definition of the sum of a function. And then you can check that this sum of function actually form a abelian group. Okay. How about multiplication? How do I multiply two functions together? Any idea? Composition. Yeah, composition. So can I define my multiplication as composition or not? Composition is not commutative. It's not commutative. I remember last time Ziqian gave an counter example to this, right? Give an example where this composition is not commutative. What example you can try? X plus 1 and x squared. You can do gf and fg. They are not the same. Okay. So composition doesn't work. Okay, so what else you can define? What else you can define? Just multiplication. Okay, you can just define multiplication. So what does it mean? So you can do f dot g x equals to fx times gx, right? So fx is a real number, gx is a real number. Multiplication in real number is commutative, is associative. Okay. Yeah. Does it make sense? Okay. If I ask you to explain, you can explain. Yeah. Cannot that means something you haven't understand yet. So you have to ask. Okay. 3. N by n matrices. Okay, n by n matrices also forms a ring. Okay. N by n matrices, how to form a ring? Does it form a ring? Does it form a ring, right? Okay. Why doesn't form a ring? Huh? Why is not commuting? Okay, the matrix multiplication doesn't commute. So this. So AB doesn't commute with. But it form a non-commutative ring. Okay. Okay, form polynomial ring over R. Okay, so this form a ring, which we will go to quite detail in this topic here, inside the ring topic. So polynomial ring will be the main subject of this topic. You will see that polynomial rings will behave feature where you can do division, where you can find the greatest common divisor. Okay, polynomial ring here will form, will behave very similarly as integer. And then you can form these formal power series, rational power polynomials, Laurent polynomials, and Lorentz series that we talked about last time. So when we deal with these, right? Last time, Siyu talked about convergence. Okay. In algebra, we don't really care about convergence here. We just care about the form of this polynomial takes. So that's why we add a word formal there. Okay, why do we add the formal there? Because we don't really see these power series as a function. We just treat it as an intermediate, a variable x. Okay, we don't really care about a convergence here. Okay, we don't really care about whether it's a function or not. We just put some variable x, that's all. Similar to polynomial rings. Okay, we don't see 1 plus x as the line 1 plus x function. Okay, we just see it as some intermediate 1 plus x. I can put 1 plus y, 1 plus z, 1 plus w. Okay, I can change the variable. It's just an algebra. Okay, the most important is the form. So, for example, formal power series is the sum from the constant term up to infinity. This is the form we want to keep. Okay, so whenever you do addition, multiplication, and so on, this form will continue. Okay? You still live in the same set. Does it make sense? We don't really see convergence or function here. We just treat it as a formal thing. It's just some variable. Does it make sense? Okay. No? Yeah. So algebra is more general because we can change the domain. We don't just see this function as function on, for example, R. In calculus, you learn R. Maybe when you go to complex, you learn C. We can put any rings inside it. Right? I can put any ring here. Then I can put all these rings here. I can put all these rings in. Okay. Okay. Yeah. So we are not restricted to any function here because later we can do more general stuff. We can put in all these rings as our domain. Okay. Yeah, so that's why we put a formal power series instead of power series. Okay, it's formal. It's just some intermediate x. Okay. Okay, so it's a good exercise to show whether these are rings or not, but we will go into detail showing a polynomial ring is a ring. Okay, today. Yeah. Not focus for this class, but I introduce here because if you go to higher level course, you will see these objects.
So read already.
Hmm?
So read already very high level.
What do you mean? What do you mean? Ring is a very common object in the maths, right? Because you met integer every day, right? Real number, these are all rings. Okay. Another thing is this one talk about already. Okay, so there's another thing is vector space. Why you ask about? Maybe I give you a big picture about these algebraic objects that you have encountered now. Maybe we don't go into detail, but let me give you some big picture here. So what's vector space correspond to these things? Maybe this slide is not too precise, but we could ask if there's anything unclear. So first, what have you met in this course? You met a group. Okay. So inside groups, you have what? You have LOC, law of composition. There's only one LOC here. Either it is addition, right, or multiplication, or some composition. Okay, which we denote maybe star. This is a group. But now we have rings. Okay, so what's the difference between groups and rings? So in rings, we have two LOC. Okay, first we call it addition. The second we call it multiplication. Okay, so where does vector space fit inside this picture here? So vector space actually fit in somewhere here. So there's 10 axioms of vector space. But the most importantly, what is in vector space? So you have one LOC. Okay, one LC is what? You have vector addition. Okay, and then what's scalar multiplication actually? This is a bit like group action, right? You are taking, for example, a vector space over R. What does this mean? Okay, so you have scalar multiplication here. So this is an extra thing. Or you have, what should I put it? So here is 1, here is 2. So second thing you have on vector space is scalar multiplication. Let's say your vector space is over R, then your scalar is R. Okay, let's say my vector space, call it V. Okay, then what is scalar multiplication here? So scalar multiplication is a map from R cross V to V. So this is like you have an R action on your V. It's a group action. So vector space is like group action plus a group. Okay. So I can change this over R thingy to other stuff. Okay. If I change R to Z, for example, then we will call this thing a module. There's an action by ring. We call it modules. Okay, so this is a vector space. You can ask about algebra. What is algebra here? How about algebra? What is algebra? I'm not sure you introduced the formal definition of algebra yet or not. So algebra actually is here. So algebra is you can have vector addition. Okay, also 2LC. You will have multiplication. You just keep addition on it. So you have addition, you have multiplication. You will also have the scalar multiplication. So algebra is the most general thing you can have. So this algebra is similar to what algebra you did in high school. What is the algebra operation you can do in high school? A plus B equals to C. Right? And then you can multiply with number 3A plus B equals to C. And then you can do 3A minus A. Right? You can do addition. You can also do multiplication. You can do 3A times A. Become 3A squared. So this is the most general thing algebra. Okay. Okay. So this abstract algebra course start with groups, the most simpler case. Okay. Of course, this group, right? There are few group action you need to satisfy. For example, identity. For example, inverses. Right. So I can do simpler groups. Meaning what? Let's say I throw away some group axiom. Maybe I say maybe there's not all of them have inverse. Then what is this object? Sometimes we call this object as a monoid. Okay, where not all elements are invertible. We call it monoid. So monoids are the things that you can just compose, keep compose only. You can just compose and compose and compose. Maybe there's no inverse there. You just compose monoid. And similarly, you can throw the identity away. Maybe there's something called magma. I don't know. There's a lot of the terminology. You can try and look for it. Magma. Okay. Yeah, MAGMA. If you throw the identity away. Yeah, some people do study this kind of stuff. Okay. And you can try and find where magma fits inside this diagram here. Where is magma? Okay, so this is just a big picture. Not too precise, but a big picture. Okay, so now you can think of vector space as a group action on some group. Scalar multiplication, you can think of it as a action here. Because you need to combine the scalar with your vector to get another vector, right? So this is like group action. And then you can check the group the group action axiom. Does it satisfy or not? Does 1 times every vector give you the vector map? Does R act associatively on V or not? So it's satisfied. You can check. Okay. Okay, so this is the big picture. So let's continue on business here. Okay, so I believe some of you who've taken the ALA have seen that your field cannot have 1 equals to 0. So let's see what happens if 1 equals 0. Let's say, what's the ring such that 1 and 0 are equal? You want to guess what is it? What happened if the additive identity equals to the multiplicative identity? What happened to that ring? The ring will collapse. Okay, the ring will collapse to a 0 ring. Okay, how to prove this? So you want to prove something is a 0 ring, right? This means you need to prove that for any element in that ring, that element is just a 0. Okay, so how to prove this? Just by a group axiom. Ring axiom. Why A times 0? So fast. So A equals to what? A equals to, you need to use the identity property right here. A equals to what? Tanya, what do you want to say? 1 times 0. Okay, but we assume that 1 is 0. 0 times A by group axiom again is 0. Okay, and this is true for all. So it collapses into a 0 ring. Okay or not? So first one is by multiplicative identity. Second is by assumption. Third is by if identity. Okay. Okay. So if 1 equals 0, then your ring collapses. If it collapses, then there's something in here is 0, and so it collapses to a 0 ring. Okay, and next question. So make a definition of unique here. So what's the unique? A unique of a ring is an element that has a multiplicative inverse. Okay. So unique is what? Unique is like 1, right? Okay. So these are the elements that you can return to 1. Okay, you can return to 1. So we call it unique. For example, what are the unique in Z? What are the unique in Z? So what elements in Z has a multiplicative inverse? Raylan, any idea? What are the unique in Z? What elements has a multiplicative inverse? Any idea? For example, 1 itself, right? 1 times 1 is equal to 1. Any other than 1 or not? -1, right? Because -1 times -1 equals to 1. Okay, so these are the multiplicative inverse. Any others? No, right? Because if you add the others inverse in, you will become a rational. Okay. 2. Let's say, how about Zi? Okay, inside here, how many uniques? The Gauss integer. What are the uniques in Zi? So what are the elements in Zi again? These are all the elements A plus Bi, such that A and B are in the Z. Okay. So what are the uniques in here? In Z? Ginseng. Eh? Eh? What did you say? Square root 2? Square root 2. Where is square root 2? My A and B are just in Z. There's no square root 2 in Z. Right? What is that? Do you know what is that? Integer? Yeah. 1, 2, 3, 0, and then -1, -2, -3, and then S9. So what are the units here? What are the elements that have multiplicative inverse? No. Is Z in Zi or not? Yes, right. So 1 and -1 must be the uniques in Zi. Okay, one of them. So any others unique or not? Any other unique? I and -I, right? Because what? What is the inverse of I? Just -I. And the inverse of -I is what? I, right? Is it okay? Nothing tricky here, huh? Okay. How about polynomial ring? What's the unit in here? What are the units in Rx? Do you know how to multiply polynomial together? You just distribute, right? Okay, yeah. So what's the unit in here? Oh, sure. 1 is in there. What else? Sure. What else? Huh? Every non-zero. Okay, every non-zero element in there. Okay, which is just R cross. Right? So which is equal to R throw away the 0. So every non-zero element, every non-zero scalar, okay, are invertible. Because you cannot invert X. Okay, so definition here. So what's the field? Okay, so what's the field? Field is a ring, okay, in which 0 is not equal to 1 and every element, every non-zero element is a unit. So we are not trying to invert 0. Okay, we are not trying to invert additive inverse. Okay, but every other thing else we inverted. This is called a field. Okay. So if we're gonna invert every non-zero element in the integer, what we get is a what? Is a what we get will be a it's a field, sure. What's that field? If we take the closure of that field, will become a rational numbers. Okay. So if we invert So if we invert every non-zero element in the integer, okay, and then we take the closure of it, okay, meaning additive closure, multiplicative closure, then we'll get a rational number. Okay. So every ring you can do this process. You take a ring, okay, invert all the non-zero element, and then take the closure of additive closure and multiplicative closure, then you will get a field. Okay. This is what we call a fraction field. Later we will talk more about it. Fraction field. This is how you get your rational numbers. I'll give you some idea. Later we will talk more detail about this. Okay, so let's go into introducing this polynomial ring. We need to do this a bit precise because we will do a lot of operation on this polynomial ring. Okay, so definition. We need to start by defining what a polynomial is. So let's define a polynomial with coefficients in a ring. Okay. Let's say polynomial with coefficient in a ring R is a finite linear combination. Combination of what? Of the power of the variable. Let's take x at the moment. Okay. So for example, fx equals to an xn plus an minus 1 xn minus 1 plus a1x plus a0. All the coefficient are in R. Okay. So for those who come late, I want to stress again, this polynomial here, you don't see it as a function. You see it as a formal thing. So it's just a variable, formal variable. Okay? Because we can sub in this R with any ring domain we like later. Okay? Don't see it as a function. Okay? Just see it as a formal thing. It's just some asn to the power n, ax to the power n, plus something. Okay? So don't see it as a function. Okay. So in this case here, we will call these polynomial as, or sometimes they are referred as formal polynomial. Okay. To distinguish them from polynomial function. Okay. We just see them as some polynomial, formal polynomial. Grace, you understand what a formal polynomial is? No. If you cannot explain like what I told the others, most probably you don't understand, right? So what's a formal polynomials? What is polynomials? What is function? To talk about function, what do you need to give? Yes, or more professionally, you will say domain and codomain. Okay, but here, when I talk about polynomial here, I don't give you domain and codomain here. Okay, so it's just a formal thing. So it's just some placeholder, some x to the power n. Because when you talk about x, y equals to x in calculus, fx equals to x, straight away you think about that function line, right? Because you are inputting some values into the function. That's why you output the graph for you. Okay. So here we don't see this. We just see this as some fx to the x. I don't know what is it. But if I change my domain, then this function will do different things for me. Okay. So this is the thing about formal polynomials. So I have freedom to change my domain and code. Okay. So we are studying a more general things. Okay. We are not restricted to continuity. We are not restricted to differentiability. Okay. Not restricted, I mean not restricted. We can have, but we are not restricted. Okay or not? Does that make sense? Okay. So this is a more general objects. Okay. So if we collect all these things, the set of polynomials with coefficients in R, in a ring R, we will denote it as, will be denoted by R square bracket X, or last time we say R adjoint X, okay? R square bracket X, or we say that R adjoint X, adjoint, ADJOIN, join and then add join, add and join. Okay, so for example, what are these polynomial rings? So we can study the integer polynomial rings, for example, okay, or the real polynomial rings, right? Okay, the coefficient I can put R, or the coefficient I can put Z. So what kind of coefficient we can put? What else? Have I killed some today? Have you been killed today? Have I called you before? I call you already. Change about Sayed. What kind of coefficient you can put here? What else? There's so many ring I gave you just now. What else? What else? What kind of ring I can put here? Zi. Okay, Gauss integer, sure. We can put Zi and join of x. Okay. Inchi, is it inchi? Inchi. Inchi, right? So what kind of ring you can put? What else? That's your coefficient. Guess what? Check the example of ring. There's so many ring I gave you. Huh? Don't know. Don't know. Very dangerous. I don't know. Wizard. What else? What kind of ring I can put? You also don't know. Don't know. Don't know or don't listen. Don't know or don't listen. Huh? Who else? Check. Jiawen. What kind? What else? What ring I can put on? What did Jiawen say? Matrix. Matrix is a non-commutative ring. If you want to consider, it's a ring as well, but it's non-commutative. So we won't consider non-commutative ring here. Sorry? How? How? It's a very good question. How? Why not? Sorry? Entry-wise, you want to multiply into a scalar? Depend on? Yeah, depend. Depend on what things you want to do. If you multiply entry-wise, like you treat x as a scalar. That depend on what you want to do. Maybe physics need this.
Didn't see before.
Yeah, I haven't seen before. But it's possible, right? From Max point of view. Fair enough. So this is the wonder of Max. You can do things you can allow to do in the framework. So what kind of X? So matrix is a ring, but it's a non-commutative ring. Okay. Yeah. But in our setting here, we deal with commutative ring. Multiplication have to be commutative. Okay. So how? Complex, right? So complex number. Okay. Or integer modulo p. Right. Okay. Or we can do polynomial ring on polynomial ring. Okay. We can do this. Right. We can attach. For example, we can let's do formal power series first. Attach x on formal power series. We can do this. Okay. Yeah. Okay, Anna. Okay. So these are all polynomial rings. So it's very general. Okay. So what time? Okay, let's define one last thing, then we take a break. So how does two polynomials are equal? How do we declare two polynomials are equal? Any idea? So remember that the polynomial we consider are just finite linear combination. Okay. So how we declare two polynomials are equal? Sorry? All the coefficients are equal. Okay. All their coefficients. Very important now, why we want to define this? Because we don't treat this as function anymore. If these are functions, how do you check two polynomials are equal? You need to check at every point. Okay, but we don't have function anymore. So we just check as long as their coefficients are equal. But it makes sense, right? Does it make sense? Okay, it makes sense, right? So mathematically, what does it mean? Precisely. Okay. So if fx equals to a0 plus a1x plus dot 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 plus anxn, and you have another g, let's say v0 plus v1x plus dot 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 plus vmxm. Okay, then fx equals to gx if and only if ai equals to bi for all the I. Okay. So for example, number 2 plus x equals to 2 plus x plus 0 times x squared. And 3 plus x doesn't equal to 4. That is. Okay. Makes sense, right? Our definition here. Okay. Okay. You don't want these two things to be equal, right? So, in other words, what? So, polynomial somehow governed by the coefficient only. Okay, governed by the coefficient. Okay, so there's a remark here. So from here, you can somehow see that the monomials xi are independent. Somehow they are independent. That's why we need to compare the coefficient. Okay, and then see here. Yeah, how about we introduce all the definition and then we take a break? Because yeah. So next we can define the degree of an non-zero polynomial. So what's the degree of the non-zero polynomial? Yes, okay. So we'll denote this by DEG Okay, so this is the largest integer, okay, and such that the coefficient an, we call it an, of x to the power n is not 0. Okay, so the highest non-zero power exists in your polynomial. Good. Then let's say you have only degree 0. What kind of polynomial is that? What happens if your highest power is 0? X0, x to the power 0. Huh? These are just the constant polynomial. Constant polynomial. Okay? But if you talk about constant degree 0 polynomial, you can also talk about 0 polynomial, right? Equal to 0. So what's the degree of a 0 polynomial? Huh? What's the degree of 0 polynomial? Should it be 0? But I can put 0 times x to the power n, right? It's still 0. So by convention, 0 polynomial is, okay, of course, it is a constant polynomial. So we will say that it degrees in is undefined. Okay, we'll just say that the degree is undefined. Undefined degree. Because you can write as 0 times x to the power 3, 0 times x to the power 6, 0 times x to the power 1. Okay. So we just say that it is an undefined degree. Okay, and then some more terminology we introduce. So should we go on? Yes, let's go on. So the non-zero coefficient of highest degree. So you have your degree, right? So that degree is a non-zero coefficient, and then we will call that coefficient as the leading coefficient. Okay, so it's like leading the polynomial. Okay, the coefficient of the highest degree, we call it leading. It's like leading the polynomial. And then we will have last definition, a monic polynomial. So what is it called, a monic polynomial? So you see mono, right? Mono is like 1. So what is 1 here? So a monic polynomial is a polynomial whose leading coefficient is 1. So for example, s squared is a monic polynomial. 2x plus 1 is not a monic polynomial because the highest non-zero power is 1, and then the leading coefficient is 2, which is not 1. Okay. Is it all right? Any question? Any question? Oh, you guys somehow changed already. You see, last time when I introduced the definition of ring, you guys can ask quite a few questions. So keep go on and change your mindset. Okay, change your thinking. You will be different when you see definition. Okay. Maybe not all of you in this class will get this ability, but please try and get it if you can. Not just if you can, actually depends on if you want or not. What's your willingness? How's your desire? Okay. Yeah, try to ask more questions, okay? Okay or not? There's a lot of definition here. Because why? We're gonna use this word later. Okay, yeah. So make sure you know this word well. Yeah, this is like dictionary. Okay, we give you a dictionary first, and then we start using this word. Later you start, most probably you don't know the word in the dictionary. So you have to come back to dictionary. Okay. All right. Okay, if no question, we can leave it to next part. So let's break until 9:07.
Yeah, so real polynomial space, 对吧 ？real polynomial.
Or polynomial with real coefficient. Okay, yeah, sure.
它是 governed by coefficient.
是，不止 real 啦，就 any ring。
Yeah.
然后
它是不是 isomorphic？可是我是不是可以找到 correspondence from Rx to R？你的 depending on your polynomial 的直接去 R。
可以。如果你要 fix 一个 isomorphism to 一个 Rn 的话，意思说你要 fix 你的 polynomial 的 degree 就是 up to 那个 n 哦。如果你要 consider 所有 polynomial ring 的话，像这个东西就是一个 R
infinity。
yes， betul polynomial ring is isomorphic to R infinity。所以 x 变成一个 grading on 那个位置哦 ，x 的 e 就是 x
，x
然后 x 就是 y， 然后 z 对，就 basis 啊。Actually I grade the standard basis 哦，就是 I differentiate e1 e2 e3 by power of n， 就这样。Yes， 不错，没错。Very good， 不会烦，这个很好的东西。这个就是research 在用的，非常好用，非常好用。
大概在高分版高一点。去 R infinity， 因为你 polynomial
非常好，good very good very good。
两个人的
还可以啦，干嘛？怎么？你有什么？
我有啊，我有选择啊，
制作人的
要不要？
没有很想要，但是我想看。
我想看啊。OK 哦，那就这样子啊，然后
OK，没有可以玩一下，还没有这样子就想啊，我想看。但是你需要给我看，你把这些名字 input 进去看，
对，
然后你玩一次给我看。
可以给我的名字
哦，
哦什么？
拍给你啊，还是你拍？Okay, Venus from here, learn here, 规则，当然，严苛，责任，没人，思语，sick，思语也是没有说 absent 是。fever，精神，圣灵，也紧绷的，怀疑，砒霜，那是砒霜，阴血缘，家业，家业离开，家，很错。 辩驳，总结，周，哎，我是定语啊，二个是定语，好吗？
两个都没有来，
两个也是定语啊，
三个也没起，一也没起，另外两个起不来的，对，两个本来醒的这样，要吗？这样，
家业 say he study 六亲，OK，真诚人，送鼓励啊，先的先，英 Grace，家业嘉文，明修，Michelle。Ryan, not here. Ellie, 雪梅 what happened to 雪梅啊 disappear for 2 days already. Yeah. 开直播了，之前开直播，有问题，零了，是蛮低的，蛮低的，蛮低哦，应该蛮低的。把那个济南那边，妈的，错一位都会有，对，叫侮辱人。这个罚的是椰子，罚的扣了啊，而且真的。但不是有罚，我来，我来，好，不是有罚，但是我来，我手一点。
嗯嗯
degree is 就是给你
我知道，就
就 degree 就是最高的
哦哦，我知道你讲什么。诶，确实，确实，确实，确实，确实，对对对对对对对对对对对对对，either 我说 highest 那个highest 就是highest，either 我说 highest power 或者我说 degree，还有
觉得
嗯，对对对对对，呃，就是我做一个 redundant 的东西，either 我说 highest power of highest power of monomial，或者说我说 degree，做其中一个。
你觉得
对啊，对，你讲的是，哎，不好意思。Okay, everyone ready yet? Okay, so thanks for eating for pointing out here. So what is highest degree means? Highest degree is unique. So there's no more highest or lowest. Okay, so what should I say here? So either I say the non-zero coefficient of, wait, let me see. The non-coefficient of the, wow, very weird. So I need the monomial. So let's say I keep the highest first. So it's the coefficient of the highest power of monomial. Monomials of a polynomial. Or I say, or I can say, it is the coefficient of the monomial So which monomial we are looking at? With power equaling to the degree of the polynomial. Okay? Yeah. So it's coefficient of a monomial. So which monomial? Okay, which monomial? So the monomial with the highest power, or the power is actually equaling to the degree of the monomial. Okay. Okay. Coefficient of a monomial. If you say I want to define what's the coefficient of the monomial, how to define? It's the number that multiply with the monomial. It's the scalar that multiply with the monomial. That's the coefficient of a monomial. Okay. So what's monomial? Huh? Monomials are the power of the variable. Some power of the variable, x to the power I. These are monomials. So we can go details up to the exact mathematical object. Okay, okay. So repeat again. I want to repeat, stress again. Matrix is a non-commutative ring. Okay, it's a very important ring actually. But in our case here, we care about commutative rings. Okay, So it's a non-example for commutative rings, but it's an example of what did I say? Non-example for commutative rings is an example of non-commutative ring. Okay, put a non in a different place. Okay, non-example of a commutative ring, but it's an example of a non-commutative ring. Okay, correct already? Correct, right? Okay, yeah. Very important rings are actually this ring. Because in physics, not all the things are commutative. Actually, non-commutative constitute a big part of this work. Okay, so maybe one day we need a matrix polynomial. Okay. What else I want to say? Okay, is it okay or not? Eating. Okay. Yeah. All right. Let's continue. So this is a big proposition for today. So there exists a unique commutative ring structure on the set of polynomials Rx, which we call the polynomial rings. Polynomial with coefficient in R. So let's say over R. With coefficient in R, we say over, okay? Coefficient over. Having the following properties. So I will tell you how we define addition, how we define multiplication. Okay. So to do this, we need to take two generic polynomials, okay, arbitrary polynomial. So you need to write down any two polynomial. So that fits into this shape. Okay, so this two polynomial might not have the same degree. Okay, but we can add them together. Let's say here we stop at n. Okay, so how do we add them? Any idea how we add them? Any idea how we add two polynomials together? You want to guess? How we add fx and gx? One want to guess? Anyone want to guess how to add two polynomials together? How about let's fill this m up to n? Can we fill that? Let's do it. Let's fill it. So make them the same. You know how to make them the same degree or not? If they don't have the same degree. You know how to do it? So for example, you should imagine this. Let's say I have fx equals to 1 plus x. I have gx equals to 1 plus x squared. How do I make them having the same? I cannot say same degree, but we can compare up to the same monomial. I just add a 0 x squared to f. Okay, then we can compare the coefficient. So why we want to do this? So how do we define the addition of polynomial? Anyone want to guess? Sorry? Component wise. What's the component here?
Coefficient wise.
Coefficient wise. Okay, that one makes sense. Okay, so we can add a coefficient with the same monomial. Okay, so you add the constant term together. We add the first powered coefficient together, and so on. Okay, so we can do this. Okay, so you should ask, if I do this, is this commutative or not? Inverse exists or not? Okay, identity is there or not? Is it commutative? Right, because your ring is commutative. Is it invertible? Because your ring is also invertible. Okay, so the most important thing here is here. You are define addition on the coefficient. Where does this coefficient live? Living in R. What is R? R is a ring. So what's the identity in this addition here? What's the identity? Zero? Yes, polynomial 0, not just 0, it's a 0 polynomial. You have to have 0 at every spot. Okay, it's a 0 polynomial. Okay, so this is addition. How about multiplication? So how do I multiply polynomial together? Fx times gx. How to multiply two polynomials together? Just distribute it. Okay, so when I multiply two polynomials together, I'll get another polynomial. Okay, but how do I compute the coefficient? What do you do when you distribute? Okay, how do you collect the coefficient? So these are just ai times bi such that I plus j equals to k. Okay, correct? Does it make sense? With this polynomial here, with this formula here. So for example, what? For example, P0 is A0 times B0. P1 is what? Maybe you take the constant from the first polynomial, multiply with the coefficient of x, the linear term from the second polynomial. Or you take the linear term from the first polynomial, multiply with the constant term in the second variable. And then so on. Okay, then you can do this for P2, P3, P4, and then so on. So these are all the ij when they add together equals to the k. Okay. So this is multiplication. This obviously commute, right? You can commute, right? Yeah, because you can consider B1 times 0, B0 times B1. So you still get the same. Commute. Associative because ring associative. Because whatever you define here is on coefficient. So this matches out what I said just now. Polynomial ring is you can just identify with your coefficient. So where does this coefficient live? This coefficient actually live in R infinity actually. Because you can have arbitrary power of x R infinity. So you can identify with the vector space or the ring. Then if you have the vector structure, vector space structure. Okay. So this is the definition you have to give. And then you need to check. So we check existence, right? Then you need to check uniqueness. Okay. So this is something starter to show. It's not hard. So let's say we have two different structures, but addition have to like this. Multiplication have to like as what we define. Then they have to be equal. Okay. So this is a unique structure. Okay. It is unique because we define like that. Okay. It is unique because it's what we define. Existence, you need to prove. Okay. You need to check all the properties. Why is it unique? Because if two structures have the same calculation, it is the same thing. Okay. It's a formal thing to show it is unique. Okay. Next, we'll talk about division with remainder. Okay, so our slogan here is like polynomial act like a integer. Okay, you can do division as well. Did you ever do division on polynomial before? The long division, right? Okay, so we're gonna prove. Are we going to prove this? Not really, but we're gonna state this. Okay, so we're gonna do long division on the polynomial rings. So let R be a ring, and then we can take a monic polynomial. Later, I will tell you why we start with a monic polynomial. And then let G be any polynomial. Okay. So, this polynomial we study them in a ring, inside a ring. Okay. So why we choose monic? It is very dependent on this ring here. So what's the result? So I have a ring. Okay. I have a monic polynomial. I have any polynomial. Okay. So what am I going to do with these three things here? So there's this a unique polynomial. Let's call it Q. Okay, and R. So why is it we call Q and R here? Q refer to the quotient, R refer to the remainder. So how are we going to arrange this? So such that any polynomial here, okay, I can split it up using my monic polynomial times some quotient polynomial plus some remainder. Okay. Does this looks like integer or not? Like 6 equals to 4 times 1 plus 2. Right? Okay. So we are trying to do division inside polynomial ring such that the remainder R, if it is not 0, it has a degree less than the degree of F. Okay, so meaning this remainder here will be something that is smaller in degree. It is smaller than degree. So we'll say that F divides G in the polynomial ring if and only if R equals to 0. Okay, so this proposition is important in the sense that we can divide. Okay, we can divide. Okay. Yes. G. I have 2G. Where's G? Where's G? Oh, okay. Thank you. So this hook should go the other way. Okay, thank you. So yeah, every element here, okay, I can divide by some monic. I get some quotient plus some remainder. So why is it monic here? Why is it monic here? Because you need to know that our ring might not have multiplicative inverse. So if it is not monic, then this thing will not hold true always. Okay. Yeah, will not hold true always. So should I give you some example? Let me give you some example here. So in ZX, can I divide? Can I do division like 3x over 2x? Can I do like this? Does there exist Q or X or not? Is there exist Q and R such that this equation is true? If 2x is not monic. What should I put here? What should I put here? When does this true? When does this equation true? 3x equals to 2x times what? 3 over 2. But 3 over 2 doesn't live in Z. Okay. So this is a drawback for a ring. So that's why we start with monic. If it is monic, I can multiply any leading coefficient I want because I'm a ring. Right? but I'm not a field, so I cannot reduce my coefficient to 1 always. Okay, sense or not? So if I want this equation to be true, I need Qx to be 3 over 2 and Rx to be 0, for example. But 3 over 2 is not in Z. Why not in Z? Not every non-zero element is invertible. Okay, yeah. Sorry.
QX plus X.
What do you mean?
QX is 1 and then RX is.
Qx is 1, Rx is X. Because our remainder have to be degree less than
Okay.
yeah. So this remainder must be something smaller in degree. Otherwise, so this is very important. So every word here is very important. Every word in proposition is very important. If you throw something away, then something will hold true. Okay. So all these words very important. This remainder here must have degree less than the degree of. Okay. Yeah. Okay. So this monic here has something to do with the ring here. If I change this R here, the scalar here to field, then I don't need to have the monic condition anymore. I can just divide with anything I like. Does it make sense? If I change the R to field, then F might not be monic anymore. Can do with anything. Okay? I don't need to start with monic F. Because I can always reduce the monic F. Right, in field. I can invert all the non-zero thing. Make sense? Yeah. So this monic thing is something to do with the ring. Okay, good. Next. So in fact, this is the corollary I want to say. So the corollary here, division, okay, with remainder can be done whenever the leading coefficient of F is a unique. Okay, so let's say in your ring, not every non-zero element is invertible, but some of them is invertible. Then you can still use it as monic polynomial. Why? Because you can invert the non-zero coefficient back to 1. Okay. So the next thing about this corollary is it can be done whenever. So what can be done? The division with remainder can be done whenever the coefficient ring is a field. Okay, coefficient ring is a field. Of course, you don't want to start with a non-zero F. Okay. You don't want to start with a 0 F. Okay. Okay. So for example, what? So for example, you can take F to be, let's say, 2x plus 1 in Z mod 3x. Okay, you can take this and then divide the polynomial in Z3x. Although this is not monic, but this 2 here is invertible in Z3. It's invertible in Z3. How to invert in Z3? 2. Multiply by 2. 2 times 2 is 4. 4 mod 3 is 1. Then you can go to other places from 1. Okay? This is not monic, but it's invertible. Okay, another thing. Corollary. Let R be a ring. And then take some polynomial GX. Okay, and then some element in R. What's the remainder? in the division of this gx, x minus a. What is this? I want you to think about this. I don't want to tell you the answer here. Think about this. If you take a polynomial, okay, and then you divide by x over n, alpha, let's say, what do you get? For example, just take an example and think about it. So let's take x squared plus x plus 1, okay, in zx. Is zx good? How about I let you try, okay, zx then. Okay, let's do zx. And then let's take x minus 2. Again, do this, divided. What do you get? What's the remainder? Okay, everyone should do this exercise. This will prove the sentence. You haven't, please forget what you learned in school. You haven't learned it yet. Try and do this exercise. Okay,
Forget it.
to advance you have to advance. Forget rings in the next course. Okay, do this, quick. Divide it, find the remainder. That one is forgetful, okay? Quick, do it. What is 2x squared plus 1? Divide by x plus x minus 2. What's the remainder? Huh? What's the remainder, Jimbo? Huh? 11. Okay, so how you write it out? So 2x squared plus x plus 1 equals to what times x plus 2? What's the quotient? Minus 2. 2x plus 5. That's all? Doesn't seem right. Oh, okay, seems right because you need to add the remainder. Plus 11, is it? Okay. How do you get this 11? Where does 11 from? Actually, it's just G alpha. If you sub 2 into this polynomial here, you will get 11. You get 11. Okay. Why is it true? Why is this true? You know why is this true? Why is this true? Why is this true in general? Yeah, why is it true? Yeah, why? So what I want to say is this 11 here, this 11 can be obtained by just substituting alpha 2 into the polynomial. So why is this true always? Yeah, why is this true always? Okay, so why is this true always? So by division with remainder, what do we get with remainder? What do we obtain? We get the equation gx equals to x minus alpha times gx, qx, the quotient, plus r, where r is the remainder. Okay, or what? What did you say? What did you say?
Substitute A inside, then become 0.
No, not yet. Sure, substitute n becomes 0, you get r. But r is what actually? The degree of r is less than x minus the degree of x minus n. What's the degree of x minus n? 1. So r has to be a constant. Okay, so r is actually a constant. here R is a constant because the degree have to be less than the degree of x minus alpha. So like what Wayne say, consider G alpha. Okay, G alpha. G alpha is equal to alpha minus alpha times Q alpha plus R, which is, so the constant R is a G alpha. Okay, so if you're gonna divide by some degree 1 polynomial with root alpha, then you just sub the alpha into your polynomial to get the remainder. So this means what? So this means that first x minus alpha will divide G in Rx if and only if the G alpha is 0. There's no remainder. Then you will divide. Okay. So why we interested in this kind of x minus alpha form? Because x minus alpha equals 0 give you the root. Okay. It will help us to split the polynomial into groups. That's why we are interested in x minus alpha. All right. So we can do general stuff. Okay. We don't restrict to one variables. Okay. We can define polynomials ring for multiple variables. Okay. It's like you're going from calculus 1 to calculus 2. Okay. You add more variable. So a polynomial in variables x1 up to xn with coefficient in R. So let's say over a ring R is what? Is the same. Is a linear combination. Okay. Combination of finitely many. Okay, finitely many. Monomials with coefficient in R. So let's reduce this word, say over R. Where what's the monomial here? So let's make it formal here. So monomial is a formal product. Okay, we don't see them as a function. We just see them as a formal product of variables x1 up to xn of the form product of power of them. So I write it as x1 to the i1, x2 to the i2, dot dot dot, xn to the in, such that all these xi living in z greater or equal to 0. Okay. And then how about the degree here? So the degree here we refer to the total degree. So what do I mean by total degree here? So the degree of the monomial here, sometimes called the total degree. I think never mind. Let's define like this first, then we will deal with it. So sometimes we call the total degree is the sum of I1 plus dot 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 plus until In. And then this polynomials form the ring of R adjoint x1 up to xn. Okay, I think I know where the confusion comes from eating, because we define, maybe we skip one definition. From here, I think I saw it. Okay, so this is a degree of monomial. Okay, so this is the degree of monomial. Just now we define degree of a polynomial. Right. Okay. So if we have the definition for degree of monomial just now, then it's the highest degree. Actually, that degree refers to monomial, not the polynomial. Yeah. Okay. Okay, I don't want to confuse the rest first. So let's deal with this, and then I will add into my lecture notes, and then we will talk about it again. Okay. By eating, do you get what I say? Yeah. I will fix something in my lecture notes and then we'll talk about it again. I don't want to confuse the rest yet. Okay, so for now, the degree of a monomial, sometimes called the total degree, is the sum of these I1 up to In. This I1 up to In is the power of this. So for example, what's the degree of, let's say, x1 to the power 2, x2 to the power 3, x3 times x3 to the power 100. What's the degree of this monomial? It's 2 plus 3 plus 100, which is 105. Okay, this is total degree. This total degree will make sense if I define the degree of the xi. Okay. Okay. Okay, so far so good. Makes sense. Everything. Okay, if okay, let's keep going for a few definitions, then we will stop. So let's delve into homomorphism and ideals. So I think today we'll talk about homomorphism a little bit. So like what I told you guys last time, when we study an object, right? We study the object itself, and then we want to study relation between objects. Okay, can I map to different objects or not? Okay, so in particular, we want to have a map between two rings. Okay, this is what we call ring homomorphism. Last time we have group homomorphism. We want to map between groups. So now we want to map between rings. Okay, so what kind of a map we are interested in? It's not just random map, right? Okay, so this map have to respect the ring structure. Okay, so last time we have group structure, there's only multiplication we need to take care. Right, one LLC we need to take care. Now we have two LLC we need to take care. Okay, so how to respect this structure here? So which is compatible with the laws. Now got two already, laws of composition. Okay, don't write it down. Okay, so what does it need to be satisfied? So such that for all A, B in my R, phi of A plus B equals to phi A plus phi B. Okay, and then definitely you need phi A B equals to phi A times phi B. Okay, so one is for addition, one is for multiplication. Okay, and then there's one extra thing we need to take care of. That is phi of 1 is equal to 1. Okay, why don't we talk about phi of 0 is equal to 0? Because that one is guaranteed by the group homomorphism property here. That one is what we prove. Once we have this, we know phi 0 to 0. But in ring, that's not necessarily true. Okay, you need to impose it. Okay, in ring, I mean, in multiplicative identity, it is not always true. So we need to impose it. Okay, we need to impose it. So what kind of example of a homomorphism we have? Okay, so I want to challenge you. Okay, so challenge you first. Try turn this equation into commutative diagram. Okay, turn this equation into commutative diagram. Okay, what do I mean by that? So I mean that you can add first and then send it across, or you can send across two objects and then add them, or you can multiply the two objects first and then send it to the other R prime, the codomain, or you can send both of them to R prime first and then add them up. They have to agree. So we encode this information into a commutative diagram. If you don't know what am I talking about, go back and check the group homomorphism. What commutative diagram I drew there. Okay, try and draw it up yourself. Okay or not? Okay. Still have time. Let's keep going. So example, what kind of ring morphism I have? So I can define a ring homomorphism from a Z to, for example, ZP. Okay, or ZP is the Z mod PZ, or I define it as a field P, field with order P. How do I define this map here? I just send X to X mod. Okay, I just send X to X mod P. What is the ring structure in Z? Just addition and multiplication. What is the ring structure in ZP? This one is something we talk about when we talk about Zn is a group. We can define A plus B mod P equals to A mod P plus B mod P, and then mod P. Okay, yeah. Similarly, you can do it for multiplication. This is also what I asked you for homework last time. So now you combine these two things together to get your ring. Okay, combine two things together you get ring. Okay, and then check that this is an homomorphism. Did you send one here to one mod P? This one gets sent to one mod P. Sure. Yeah, one mod P equals to is the identity. Yeah. Okay, and then you need to check is xy gets sent to xy mod P, right? Is xy mod P equals to x mod P times y mod P mod P? Right, this is the thing you see in the number theory. Okay, yeah. Is it true that x plus y mod P equals to x mod P plus y mod P mod P? This is what you need to check. So if you learn well from your number theory, or maybe discrete math, you should see it also. Those you prove, right? You prove them, it's true, meaning you have a ring. Okay. You only prove something here, but actually you have a ring homomorphism. Okay, so these property get encoded into a information of a map. Okay, you study it as a map, ring homomorphism. Okay, we can stop here actually. If you have question, you can deal with it. Any question? No? Any question? Yes. What do you mean by it? Oh, you mean for these two equations? You mean do you split? Yes. So for each of these equations, you can draw one commutative diagram. If you want to put it together, it's okay, but very messy. That's very messy. I mean, no. You shouldn't do that because you will have two maps in the same arrow. So split it. In the next class, I will address the degree of function and degree of polynomial. Degree of a polynomial and a degree of monomial. Okay, we'll make these two things clear.